Hello again, everybody. Welcome back. Today we're in section 3.1 talking about measures of central tendency. So one very important idea in statistics is to be able to describe a typical value or a central value. So today we'll talk about some of the ways that can be done. We'll talk about how to determine the arithmetic mean of a variable from raw data. Now, arithmetic mean is just what most people call the average. We'll also learn how to determine the median of a variable from raw data, and we'll explain what it means for a statistic to be resistant, and we'll talk about how to find the mode of a variable from raw data. So here we go. First off, we have the arithmetic mean. Now, there are different types of means. There's arithmetic mean and geometric mean, and there are probably some others, but the only one that we're really going to use in this course is the arithmetic mean. So this is the only time you'll ever hear me talk about arithmetic mean. Usually we just say mean. And when we say mean, it means average. Most people think of an average as the sum of a set of values divided by the number of values you have. So that's what we're talking about here. The arithmetic mean, which we usually just call the mean of a variable, is computed by adding all the values in the data set and dividing by the number of observations. So we add all the values together and divide by the number of observations. That's what you've always called an average, but from here on out we will call it the mean. So when we want to refer to the population mean, we use the Greek letter mu. This is the lowercase Greek letter mu, and it looks like our letter U with a tail on the front. And it actually serves the same purpose as the letter M in our alphabet. So M for mean, M for mu. So population mean is computed using all the individuals in the population, and population mean is a parameter. Remember we talked about in chapter 1 how when a number represents a whole population, it's a parameter. So the Greek letter mu stands for population mean, and it is a parameter. Now, sample mean is represented by the symbol X bar. It's just a letter X with a bar over the top of it, but when we read it, we say X bar. This is computed using sample data. And the sample mean is a statistic. So remember, X bar is the sample mean, and it is a statistic. And the way you keep this straight is S for sample, S for statistic, P for parameter, P for population. And we typically use Greek letters to represent parameters, and then Roman letters, or what would be regular letters to us, to represent statistics. So now let's look at the formulas. I know that we all know how to calculate an average, but the formulas look a little different. So here is the formula for population mean. And you can see that you just add all the numbers together and divide by the population size. We have seen this capital N before. Capital N always stands for the population size. But look at this. Instead of writing out plus, 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 this capital sigma is the Greek letter that stands for sum. And this is not just in statistics. In all of math and science, the capital sigma stands for sum. When I taught high school, my high school students used to call this capital sigma that E thingy, but it's not an E thingy. It's actually similar to our capital letter S. So it's the Greek letter sigma, and S for sigma, S for sum. So when you read this, you say the sum of all the X values divided by the population size. So the population mean is the sum of all the X values divided by the population size. And now this subscript I here just means that we're going to do the first one and the second one and all of them until we get to the last one. Okay, then the sample mean says that X bar is equal to the sum of all the X values in the sample divided by the sample size. So again, both of these are calculated the same, but in the population mean we divide by population size, and in the sample mean we divide by sample size. Okay, time for an example. This says the data in the table represent the first exam score of 10 students in introductory statistics. Treat the 10 students as a population. And note this, when dealing with decimals, always round computed values to one more decimal place than the original data. Now, if it comes out whole, we can leave it whole, but if it comes out with decimals and we have to round, we will round to one more place than what the data had. This data has no decimal places, therefore our answer can have up to one decimal place. Okay, here we go. Computing the population mean. We know that to do the population mean, we add all the values and divide by the number of things in the population. So I don't want to write all of these values down. What I'm going to do is just write the sum of all the x values is 790. And I've already summed these on my calculator. So, you know, when you're showing your work in MyLabs Plus, I do not expect you to type all of these numbers. That would be too tedious, and it would defeat the purpose of being able to use a calculator. So we're just going to say the sum of all the x values is 790, and then I'm going to say that mu, that is population mean, equals the sum of all the x values over population size, and that equals 790 over 10, and that equals 79. So in this case, we actually did not need to round off to one decimal place, so that's fine. But also, I just want you to know that when you're asked to show your work for computing a mean, this is how you show it. You say the mean is the sum of all the values divided by the population size, and you give the two values and then you give the answer. Now let's look at part B. This says find a simple random sample of size n equals 4 students. Now I don't know if you've got your random number table handy. I know I don't have mine handy, but we need to get a sample of 4 students. What we could do is put all 10 numbers on a slip of paper and put the slips in a hat and draw the numbers out of a hat. That would be one way to do it. Or I happen to have my graphing calculator here, so I'm just going to get a random sample of 4 numbers between 1 and 10 from my calculator. And this is what I got. Now if you got a simple random sample from your calculator, your 4 numbers would be different. That's okay. You're not going to be asked on a quiz or a test to generate a random sample of 4 numbers because there's no way to grade it as right or wrong. But let's just use this sample. Now this is giving us number 7, number 1, number 4, and number 8. So that would be Joel's score, Michelle's score, Pam's, and Sam's scores. So 74, 82, 71, and 84. And now in part C it says compute the mean of the sample. Well, we can add those 4 numbers together and we see that the sum of those 4 values is 311. So now the sample mean x bar is found by taking the sum of the numbers and dividing by the sample size. So that's going to be 311 divided by 4, which is going to come out 77.8. Now I know on your calculator it says 77.75, but remember that when we're calculating statistics, we round to one more decimal place than what's showing in the data. So I just kept one decimal place here. Now let's talk about the median. The median is another measure of central tendency, and again, this is valid only for quantitative data. The median of a variable is the value that lies in the middle of the data when arranged in ascending order. We use the capital letter M to represent the median, and we do not have different symbols for population and sample here. Here are the steps for finding the median of a data set. We'll arrange the data in ascending order, that means from smallest to largest. We'll determine the number of observations n, and then we'll determine the observation in the middle of the data set. The reason we have to determine the number of observations is that our method is going to vary based on whether we have an even number of observations or an odd number of observations. So if the number of observations is odd, then the median is the data value that's exactly in the middle of the data set. In other words, the median will be the observation that lies at the n plus 1 divided by 2 position. If the number of observations is even, then the median is the average of the two middle observations. Now let's do example 2 together, and we want to find the median of a data set with an odd number of observations. Then in example 3, we'll find the median of a data set with an even number of observations. Now remember, this has to be done when the data are in order. For a short list like this, it might not be too much trouble to put the numbers in order, but for a bigger list of numbers, you might want to go ahead and use the sort A function on your calculator. So I believe we have 9 values here, and I'm going to go ahead and sort these 9 values from smallest to largest. Okay, now you probably can look and just see without any calculation at all that 217 is the number in the center, because 217 has 4 numbers that are less than it and 4 numbers that are more. So 217 is definitely our median, but for a longer list of numbers, it might not be so easy to just look and see the middle value. So let's go ahead and do it the official way. The median is going to be the number that's in the 9 plus 1 over 2 position. Remember, we do n plus 1 over 2. So 9 plus 1 is 10, 10 over 2 is 5. So we want the number in the 5th position, 1, 2, 3, 4, 5. That's our median. And again, notice that there are 4 numbers below it and 4 numbers above it. Now this data set has 10 values, so our method is going to change a little bit. Again, let's start by putting all of the numbers in order from smallest to largest. And now you can see that there's not one value that's in the center of the data. If we took 77, you can see that couldn't be the median because there are 4 numbers less and 5 numbers more than 77. So since we have an even number of values, we will average the 2 middle values, the 77 and the 82. So 77 plus 82 divided by 2 is 79.5. So our median is right in between the 2 middle values. And now you can see that there are 5 values less than the median and 5 values more than the median. Now I want to show you how to calculate the mean and median of a data set using the statistical functions on your graphing calculator. Now I'm going to assume that you already know how to use the list editor, and if you don't, you'll want to see the calculator introduction video that I have posted in Canvas for you. But if you already know how to use the list editor, then pause the video and enter these 10 numbers into your list 1. And I'm going to just press stat here and show you that I already have those 10 numbers entered in my list 1. There they are. So now you don't have to do this from the list screen. You can do it really from any screen. To get the calculator to find the mean and the median for you, what you're going to do is press stat, then arrow over to the calc menu. So press the right arrow one time to go to the calc menu. Then what we want to do is run the one variable stats command. So that's already selected when you pull up the calc menu. So just press enter. Now here's where things can get a little different. If you have the old calculator operating system, then this is what you'll see. And the calculator is waiting for you to tell it what list you want to get the statistics for. If you don't tell it a list, it will assume that you want list 1. But if you've used any other list, you would need to press the second button and then the appropriate button down here to indicate which list. Notice the blue markings above these keys say list 1, list 2, list 3, and then lists 4, 5, and 6. Now this is why I always keep my data in list 1, because I like to be able to just run the one variable stats command and not have to specify which list I'm using. So I'm going to go ahead and press enter. And now let me show you what's on this screen, and then I'll go back and do this again for people who have the new operating system. So people with the new operating system, just hang with me for a minute. Here at the top we have X bar. Now you have to remember that the calculator does not know whether our numbers are to be considered a population or a sample, but both means are calculated the same way. So the calculator just uses the symbol X bar, but you have to know that if this is a population mean, when you write it down, you really need to label it mu instead of X bar, but this is the mean of whatever's in list 1. Notice right here is the sum of whatever's in list 1. So if you were on a show your work type of problem and you needed to show how you're calculating the mean, you could use this sum function to get the sum and then just show that you're dividing by the number of values in your data set, which is given right here. So mean and then sum, and then this is the sum of the squares of each data value. We don't need that right now, so just disregard that. And we're going to talk about these other two values in section 3.2. But now notice that we have a down arrow here, so you could click the down arrow to scroll on down, and notice that there's a whole other screen of values down here. So after n equals 10, we see that the minimum value in our list is 62, the maximum value is 94, and the median is 79.5, which I believe is exactly what we found on the previous slide. And here we have values for Q1 and Q3 that we will talk about in a later section. Now arrow back up and let's just kind of make sure we understand. The top line is the mean, whether it's population or sample mean. They call it X bar, but you have to label it mu or X bar depending on whether it's a population or a sample. Then we have the sum of all the values here. And then we have the number of values in our list. And then arrow down. On the next screen we have the median. Okay, so I've cleared off everything that we had before, and now I want to talk to the people who have a newer model of calculator. So your operating system is a little bit different than the old operating system, and it's actually a little bit friendlier. So let me show you what's going to happen. You also are going to press Stat and arrow over to the Calc menu, and you're going to press Enter to run the one variable stats command. Now it's asking you which list your data is in. So by default it should be set to list 1. And now on the second line it's asking you where are your frequencies. Well, we don't have any frequencies. We just want the calculator to use each number one time. So you actually need to delete that. You can leave that blank and then arrow down and press Enter to calculate. And now you can see that we have the same values that we got before with the old operating system. You too can arrow down and see the median, but you just have to know how to handle that screen where it's asking you what lists to use for each thing. So let me go back to it one more time. Stat, Calc, one variable stats, and then it's going to ask you where are the numbers that you want to get the statistics of. Well, our numbers are in list 1. And then on the second line, it's asking you where are the frequencies. Well, we don't have any frequencies stored. We just want the calculator to use what's in list 1. So leave that blank, and then you'll just arrow down to calculate and press Enter. Okay, now we want to talk about what it means for a statistic to be resistant. You know, we have two measures of center now. We have mean and median, and it stands to reason that if we have two, then one of them is going to be better for some things and the other one's going to be better for other things. So let's look at the data set we have here in example 5. Yolanda wants to know how much time she typically spends on her cell phone. She goes to her phone's website and records the call length for a random sample of 12 calls shown in the table. And here are the 12 calls. So it says find the mean and median length of a cell phone call. Which measure of central tendency better describes the length of a typical call? Okay, so you could do this on your calculator. You could just, for practice, go ahead and enter these 12 numbers, and I won't show it again, but I'll just say that the mean of those 12 numbers is 7.3, and the median is 3.5. Now, just looking at these 12 numbers, which of these two do you think is a more typical value? In other words, which of these two better represents most of the numbers that you see here? Well, if I look at the X bar number, I only see one number that's more than 7.3. All of the other numbers are less than 7.3. So I don't think we can realistically say that 7.3 does a good job of representing these numbers. On the other hand, 3.5 does seem to do a fairly good job of representing these numbers because some of them are less and some of them are more, but none of them are very, very far from 3.5 except for the 48, which is very far away from all the other numbers. Now, if the 48-minute call was really a 5-minute call, what would be the new mean and median? So you can go back in your list editor, take out the 48 and replace it with a 5. So you can go back in your list editor, take out the 48 and replace it with a 5. And when you run one variable stats again, the new mean will be 3.7, but the median will still be 3.5. So what happened here? Well, remember that the median is just the number that has the same number of values above it as it does below. So when we replaced the 48 with a 5, we were replacing this 48 with a number that is on the same side of the median, and so the median did not change. But the mean changed because taking out this large value and replacing it with a 5 caused the sum of the numbers to be much smaller, and therefore the mean was smaller. Now I've copied onto this slide the numbers that we had on the previous slide, and again notice that the extreme value of 48 had no effect on the median. The extreme value did affect the mean. Removing the 48 caused the mean to change quite a bit, but the 48 did not have an effect on the median. So a numerical summary of data is said to be resistant if extreme values relative to the data do not affect its values substantially. So the median is resistant because the presence of extreme values does not affect the median very much, but the mean is not resistant. So remember we talked in Chapter 2 about right-skewed data and left-skewed data? Well, when data are skewed, there are extreme values in the tail, and that tends to pull the mean in the direction of the skew. In the example we just looked at, the extreme value of 48 pulled the mean to the right on the number line, and that made the data right skewed. So here are three curves, one that represents left skewed data, one that represents bell-shaped data, and one that represents right skewed data. Remember that the mean is not resistant, so when the data are skewed, the mean is going to get pulled farther in the direction of the skew, and the median might get pulled a little bit, but it won't get pulled very much. With bell-shaped data, the mean and the median are generally the same. They may not be exactly the same, but they are generally the same. That is, they're both found in the center of the distribution. And then with right-skewed data, we see that the mean gets pulled far to the right, where the median gets pulled only a little to the right. So with left-skewed data, the mean will be smaller than the median. With right-skewed data, the mean will be more than the median. And with symmetric or bell-shaped data, the mean will be about equal to the median. Therefore, for skewed data, the median summarizes the data better than the mean, because the median is resistant where the mean is not. And like we said before, the mean and the median are roughly equal for symmetric data. So you may be asking yourself, if the median does a better job of summarizing skewed data, and either the mean or the median could be used to describe symmetric data, why even bother with the mean at all? And the answer is the mean is still very important because many inferential methods are based on the mean. So whenever a data set is skewed, we will use the median to describe the center of that data. But when a data set is symmetric or bell-shaped, we will use the mean to describe the center of that data. Now I want us to look at example 6 together. This says the data in the table represent the birth weights of 50 randomly sampled babies. Find the mean and the median, describe the shape of the distribution, and decide which measure of central tendency better describes the average birth weight. So let's start by calculating both the mean and the median. So we'll say stat, calc, one variable stats, and then I have mine set on the new operating system. If yours is the old operating system, your screen will now say one variable stats, and you can just press enter. But I'm going to arrow down and press enter here, and you can see that the mean of this data set is 7.49. Remember, we round to one more decimal place than what the data showed. So the mean would be 7.49, and now I'm going to scroll down and get the median, and the median is 7.35. So there's not a lot of difference between those two, honestly, 7.49 and 7.35. So in part B, where it says describe the shape of the distribution, so we'll have the calculator graph. And here, mine is set on the standard window, so yours may not look exactly like this, but we would like to have the calculator zoom in on the histogram for us. You can see that part of the histogram is visible on my screen. So I would like to show you this zoom function. If you press zoom and then you scroll down to option 9, you can see that option 9 is zoom stat. And that will zoom in on whatever statistical plots you have turned on. So you can either scroll down to that and press enter, or you can just hit 9 and it will automatically execute it. And so now you can look at this and see that it does look a little right skewed. I would be inclined to say that this data is right skewed, except that we've already looked at the mean and the median, and we know that they are very similar. So that's got me wondering, would it be possible for this data to be arranged in a histogram that looks more symmetric than the one we got? So now I want us to kind of play with the window just a little bit. Let's press window, and let's set our X-min on 5.5. I know that our smallest value is 5.8. But what I want to do is set the calculator to have a class width of 0.5. So I'm going to set X-min at 5.5. And our largest value is, I believe, 9.8. If you look back over here, it's 9 point something, maybe 9.4. Well, let's set the Y max at 9.5. I believe that covers our largest value. And then we can arrow down. I'm thinking a class width of 0.5 will be appropriate. And Y-min, remember, never needs to be less than 0. And Y-max is a guess at this point because I don't know. I don't have a frequency distribution to look at, so I don't know for sure how tall the tallest bar is. But I'm going to guess that it doesn't need to be any more than 20. And now I'm going to graph again. And this time when I look at the histogram, you can see that it does look a little more symmetric. So I think that since the mean and the median are so close together here, and we are able to get this symmetric view of the histogram, I would say that the mean does a better job of describing this data than the median. So just remember that we use median when the data is clearly skewed, but otherwise, if we can't say that the data are definitely skewed, we always revert to the mean. And now we have a third measure of central tendency, and that is going to be the mode. And mode can be computed for either quantitative data or qualitative data. In fact, every time you've ever seen an election where they have to count the votes to see who won, what they're doing is finding the mode of the votes. The mode of a variable is the observation that occurs most frequently. A data set may have no mode, or one mode, or more than one mode. If no observation occurs more than once, then we say the data have no mode. Here's an example. This says the following data represent the number of O-ring failures on the shuttle Columbia for its 17 flights prior to its fatal flight. Find the mode number of O-ring failures. Well, since we have the data sorted in order from smallest to largest, it's easy to see that the value that occurs most often is 0. So the mode of this data set is 0. Some people might mistakenly try to say that 1 is also a mode, but 1 does not occur as many times as 0, so we would not say that 1 is a mode. Now let's try to find the mode of this data set. Here we have these scores that we've seen before, and the easiest way to find the mode of a data set is to put the data in order from smallest to largest, which I've done here. And when the data are put in order, you can see that no value in this set repeats, so we would say that this data set has no mode. And here's example 9, and this is a table of qualitative data. You may remember this table from section 2.1. This says the data in the table represent the location of injuries that required rehabilitation by a physical therapist. Determine the mode location of injury. So the easiest way to determine the mode is basically to make a frequency table, which we did back in section 2.1, so I won't ask you to do that again, but I'll just go ahead and make the frequency table for us. And now you can see that the injury that occurred most often was back. It occurred 13 times, and no other injury occurred as many times. So the mode of this data set is back. Now let's summarize the 3 measures of center that we have seen in this video. We've talked about mean, median, and mode. Mean is simply what most people would call an average, but we do have 2 different symbols. For the population mean, we use the Greek letter mu, and for the sample mean, we use x with a bar over it. We say x bar. And the mean is simply calculated by summing the data and dividing by the number of observations. The median is the middle number when the data are arranged in ascending order. And then the mode is the value that occurs most often. And now, just as important as knowing how to calculate each one is knowing when each one is appropriate to use. If you have qualitative data, mode is your only choice. If you have quantitative data, your primary choice is between mean and median. We really don't use mode all that often for quantitative data. But if you're trying to choose between mean and median for a quantitative data set, then you want to look at the distribution of the data. If the distribution is symmetric or nearly symmetric, then go with the mean. But if the distribution is skewed, then go with median.